In this next set of videos, we're going to be talking about wall clock time analysis with the Purview tool. Wall clock time is often the most interesting metric to you because it's the time that an end user sees your application taking, and so is very directly impactful to the end user. It's a little bit harder, however, to do an analysis of wall clock time. So if you know your application is CPU bound, you could probably just go directly to a CPU analysis. In order to do these tutorials, we need a demo program, and that is what this block time. I've created an application called block time, which is this demo that we're going to use. And here is an example of the sort of kernel of what this application does. It's basically find stir. It fetches a set of directories recursively, and then it gets the files in each of those directories that match a particular file pattern, and then for each of those files it reads every line in that file looking for a text match of a particular regular expression. If it finds a text match, it will then add the file to a results list. So this is sort of what find stir does. It goes and searches an entire directory hierarchy for a particular regular expression and then remembers which files were found. The important aspect from our point of view is simply that we have an application that is not likely to be just CPU bound. It is likely to have both disk, some non-CPU, in this case disk, as well as CPU time. And that's our application. The most important thing that you need to know in order to do a wall clock time investigation is that you need to collect more data than is collected by default. So if I go to the collect menu and I click through the elevation, I'll get this standard collection dialog box, and you can see that there's this thing called thread time which is not clicked. You need to select that. Older versions of Purview, this is called thread blocking. It's the same thing. So you need to click on this thread time in order for Purview to collect the extra events necessary in order to do a wall clock time analysis. When you do this, you can actually click on this and you can find out more about thread time, and you can see that it will talk about the wall clock time investigation, and it will give you help getting started. And so you need to click that, and then otherwise it's just the same as it was before. I'm not actually going to perform a collection. In order to speed things up, I've already pre-collected this particular scenario, and it's this block time sync.etl.zip file that was created when I did that. Now, when you do a block time analysis, when you turn on that thread time option, you'll get three new views: these thread time stacks, thread times with ready thread, and thread times with tasks. In this video, we're only going to talk about this first one, thread time stacks, and as its name implies, it's showing me what every thread is doing at any instant of time. We only care, as with all these ETL-based viewers, it's system-wide, and we only care at this point about a particular application, the block time application. So we'll zoom in on that, and then I'm going to go to the call tree view. At this point, this should start to look very familiar because it really is the same viewer that was being used for the CPU analysis. The only difference is that instead of showing you CPU milliseconds of time, it's showing you real time or clock time for every thread. So that every thread part is really important. We have 4 threads, and you can see that they all sort of start very early, about 400 milliseconds of the trace, and they all end about 10 seconds in the trace, and therefore they have about 10 seconds worth of clock time for each thread, and then those all add up to this number, which is our total metric. So our total metric is actually the accumulation of 4 different threads clock time, because Purview doesn't know what's interesting and what's not interesting. And it turns out that most of this clock time, in particular the clock time associated with these 3 threads, is not likely to be very interesting. You can see that they only have 5 milliseconds, 2 milliseconds, and 1 millisecond of CPU time associated with them. whereas the startup thread has almost 2 seconds of CPU time. So it's probably the one that's doing the work. But this shows the next most important aspect of a wall clock time investigation, which is that you must narrow your range of focus. If you grab things in aggregate, you'll get these aggregated situation in which uninteresting time, like the things that are the finalizer thread is doing, blocked waiting for the next finalizer event, get mixed in and weighted the same as important things like what I'm doing with my scanning of the disk. And so we have to find a way of separating out the parts that we're interested in from the parts that we're not. And sadly, that's scenario specific. There's no general way of doing that, or Purview would have done it for you. So this is where you have to step up and do something special. And so in this particular case, we have a very simple scenario. In service scenarios, it's often very complicated. You have lots of threads doing lots of things simultaneously. And in subsequent videos, we'll talk about how to get through all of that. But in this particular case, it's pretty simple. We have one main program, and so I'm going to search for main. And you can see here it is, my block time main program. And you can see that it is always on one thread, and it's always over a particular region of time. So I can select these two regions of time and do set time range. And what that does is now narrow the focus to just the time range in which the main program is running. And then I'm also going to select the thread of interest, in this case the one that has main, and I'm going to right click and do include item. And you see now, you'll see that no other thread is available. And you can see that our total metric dropped from almost 40 seconds down to this 9.7 seconds, which is the time that was in the main program, in that function, or any of its or any function that it calls. We now know the real time or the clock time associated with where that time went. And so let's go ahead and click in a little bit, and you'll see that up until I get to this line right here, this ugly method right here, I'm still basically have all my clock time is spent in this call stack up to this point, at which point it breaks up into pieces. Now I'm going to clean up this view a little bit by folding away anything that's less than a 0.1%, and that gets rid of little tiny things that is probably not very interesting. And so you can see now that there's this ugly little method called block time program brackets C underscore display class 1 blah blah blah, and it in turn breaks up into 4 pieces. So there's a couple things to talk about. First, what is this ugly looking method? And we can answer that question by using the go to source functionality. And when we go to the source, we'll see the line numbers associated with those that time, and where each line has been attributed with the time associated with that line. And you'll see that that function is actually this anonymous delegate. So I created an anonymous delegate which I passed to this function called doWork, and that function has no name, right? That's the whole point of being an anonymous delegate. Well, the C# compiler made a name for it, this C underscore display class blah blah blah. And one of the nice things about the name that it creates is that it always uses the name of the method that it's inside. So because this anonymous delegate was inside scan directory, it used scan directory as part of the name of this anonymous thing. And that helps you find it, even if you didn't have source. So this is showing me that there was this, the kernel of my search is actually in an anonymous delegate, and it's the thing that's using up all the wall clock time, which is not terribly surprising. And that it breaks up 4 ways effectively, and you can see that the lion's share is being spent, 70% is being spent in read lines, 16% in move next, 11% in get directories, and 2% in regular expression matching. And so this gives me a really good idea of what I need to optimize in order to reduce the wall clock time. Another useful thing to know about these views is that the when field does work properly, and the when field, as you recall, tells you, gives you numbers. It acts like a little graph, whereas each digit in this stream is this time, in this case 305 milliseconds long, and a 0 means that it's using 10% of the thread times, a 2 means it's using between 20 and 30%, 9 means that it's using between 90 and 100%, and A means it's using over 100%. And so this, at the topmost level, you would expect the thread to always be using 100% of its thread time somewhere. And so these should all be A's or 9's, where if the round off error was a little bit on the low side. And then it splits up, and you can see that, oh, the read lines is spending on the average 70% of the time, but you can see that it goes up and down over time. So the when field is often quite valuable. The other thing that's valuable is that we have these pseudo nodes at the end of each of these. At the end of each stack, the Perfview puts a pseudo node on here that tells it what kind of time was being spent. In a CPU view, you didn't need to have this because everything was CPU time. Well, now I have different kinds of time, and so I indicate that by this label. And the most useful way of using this is in the by name view. If I click over to the by name view, I get this actually very nice summary. It tells me that 18% on the average over the entire application, over that area of interest, or over that thread that I've narrowed it to, 18% of my time is CPU, 65% is block time, 13% is hard faults, and only little less than 1% is disk time. This might surprise you because you'd expect actually disk time to be most of it, and there's a good reason for that, and I'll talk about that in subsequent videos. The bottom line is that the disk time is being done by someone else, and we're just waiting on that someone else to finish, and so that disk time becomes block time, and that's why it is the way it is. Another useful thing is that hard faults are, for those who don't know, hard fault is the case when you're trying to access something that's in memory but is not actually physically present yet. It's actually been paged out to the disk. And so what it has to do is it has to stop, fetch that data from the disk, and then it can continue. So it is a kind of block time, but it's a very specific kind of block time. And I want to show you by doing a go to call ers, is that page faults and disk I/O does the same thing, is that it has additional pseudonodes associated with it. So in particular, this hard fault was always associated with a particular file. And in this case, this file is a directory file, and this was actually fetched from this stack. And so I was in this get directories when I produced this page fault. And if you wanted to, you could drill into this other category here and what's going on inside the operating system. But what you're going to find is that the operating system has mapped the directory entries as a mapped file. That is, it looks like it's in memory, and it's page faulted in, not file IO'd in order to get those directory entries. So when we're scanning the directories, we actually cause page faults to happen to get the entries that we're interested in. So that's why we have page faults. Often page faults are simply parts of your executable that were on the disk that need to be pulled in from the disk just to execute code. But in this case, the page faults are actually directory entries that we were fetching. So the other cool thing that you can do with this is that if you just wanted to find out, well, all right, I want to understand my CPU time in a little bit more detail, I can select CPU and then hit include item, and now I've removed everything that doesn't have CPU time in it, and notice my metric has dropped from about 10 seconds to about 1.8 seconds. And now I can go back to my call tree and I can see, oh look, if I only cared about CPU time, I actually get a very different layout where the move next is now the lion's share. And in fact, regular expressions went from only like 2% up to 10% of the total time. And so this allows me to do a CPU investigation if I wanted to And then when I'm done with that, I can just sort of undo this by going back, and then I can look at it what's going on from a full time all up, any kind of time, including block time. So this shows you the basics that you need in order to do a block time investigation. And in review, it's important first that you need to collect. You have to click this thread time checkbox in order to get the information. Once you have it, cancel this. You'll have a zip file that has some extra views, and we talked about the thread time view and how the most important thing that you need to do is find an area of interest and get rid of all the other thread time that you're not interested in. And we did this in this case by zooming in on a particular method, but there are other techniques, and we'll talk about those in future videos.